Hey everybody, I just wanted to put together a little video just sort of showing you what you need to do for each of these sections in the lab, since the majority of you seem to be pretty confused going into each lab. So as always, I'm not going to, well, I was going to say, as always, you need to read the lab. So that means if you don't have a lab book, that's part of the reason why you're so confused. You need to get a lab book, you need to read the lab. Read the procedures, read the experiments, pretend you were going to do all of those things. Watch the video so you can see what each of these reactions is about. Now, what is happening here is that we are reacting metals with different metals. We're reacting metals together and seeing if they form reactions. By reaction, we're looking for evidence like bubbles or precipitation, something forming, color change, that kind of thing. So I've labeled these as reaction or no reaction. Your task here in these first two parts of part one is first to just write a balanced, equation. Come on. Balanced equation. Okay? And you're going to pick a reaction from up here that says RxN, not one that says no reaction. So you're going to pick a square that has a reaction, and you're going to show how that metal and that other metal reacted together. Okay? That's all you have to do for this part. Pick one, write a balanced molecular equation. For part three, or I'm sorry, for number 3 on part 1, you're going to rank all 6 metals. Now, some of you only see 4 metals. There are 6 metals. They are magnesium, zinc, copper, lead, hydrogen, and silver. Okay? You'll notice that there are no reactions when we react, let's say, lead with lead, right? It's the metals are both lead, so nothing's going to happen there. It's the same metal. So we're only looking for pairs where reactions happen or don't happen. Okay, once you've gone through and looked at all of these reaction results, we're going to rank them from most active to least active. So pay attention. The most active metals have reactions with other metals. Okay? When you are reading this table, there are 2 ways to read it. Okay? When you see reaction, that means there was a reaction when magnesium reacted with silver nitrate. That means magnesium is reactive. That does not mean that silver is reactive. Okay? How do you know? Because if this reacts, we're going to get some switching of partners. If this reacts, then magnesium will be the thing paired with NO3 instead of silver. Okay? If there's no reaction, then silver stays paired with the NO3 and magnesium stays as magnesium. In that case, we would say that the silver was more reactive. Whoever ends up with this NO3 is going to be the more reactive one. And in the situation here, whoever ends up with the chlorine will be the more reactive one. Your task is to rank them based on your observations in these results. Okay? It looks like, and this might be helping you a little, that at least where it's concerned with silver nitrate, that magnesium, zinc, copper, and lead are all more reactive than silver, because when paired with silver, we see reactions. Okay, that's part 1. Part 2. Part 2 has a few different reactions happening. So the first one was single displacement. Now we're going to look at double displacement. And so this is a question that you guys can answer. So I've gone ahead and filled in some data for you. So in each of these, we have some cations that are all paired with NO3 minus, meaning that when we were to go and get bottles of each of these things, we would get ammonium nitrate and copper nitrate and iron nitrate and potassium nitrate. Okay, all of these are the positives that were paired with nitrates. On the top are all of these negatives. These were all paired with sodium, meaning that this was sodium chloride, sodium sulfate, sodium acetate, sodium carbonate. Now, when we mix these things together, we're going to get 2 new products. Okay, so for example, in this square right here, we're mixing sodium chloride with ammonium nitrate. Now we're going to get two things. We're going to get the result of these guys pairing together, the ammonium chloride, and we're going to get sodium nitrate pairing together. In almost every situation, one of the two things you form will be sodium nitrate. The other thing is what we're interested in. Sodium nitrate, by the way, is not soluble. Is always soluble. I was going to say it does not form a solid. So this isn't of any interest to us. But all of these other pairings, the pairings of all of these metals in that column, the pairings of all of these compounds here, they are what we're seeing results for. So S written here means that it's soluble, so no solid formed. An I or an SS, they sort of mean the same thing here. These mean that we were seeing some cloudiness or the formation of a solid. That would indicate that these things are insoluble. And so what you're going to do is look at this table and then write some general rules. So just to give you, oops, erased too much. I think that was an S. So if we look at, oh man, I did erase too much. If we look at, let's look at the rule for hydroxide. So that's for F, hydroxides. As we go down this column, it looks like for the most part we've got a solid forming, a solid forming, solid forming, solid forming, solid forming. There were three cases where there was no solid forming. So what we could say for hydroxide generally is that mostly compounds that contain hydroxide are insoluble, with three exceptions, right? And in this case, the three exceptions are NH4 plus when paired with sodium hydroxide, K plus, and Mg2 plus, right? Because those are the three exceptions. When we write the rule for acetates, it looks like they're always soluble. That's what you're doing. You're writing the rules based on the table, not rules based on your solubility lists on your formula sheet or from your book, okay? From this table of data. All right, for this page, you guys are choosing two of the reactions from that table that I just showed you. So two of these reactions that produced, solids, so any of the I's or SS's, and you are going to write balanced equations. Notice that you're writing two balanced equations, okay? They have to have formed a solid. You're going to write the entire equation, all right? Balanced. Part 5, or question 5, this refers to part C of the experiment, where you guys are mixing things in big test tubes. And again, those, you're going to write what you saw, or write what Andy says happened when these two mixed. I'll give you a hint. One releases heat, one produces gas. And then you're going to write those equations. Again, balanced equations. This is an equation writing lab, right? Chemical reactions 2. Single displacement and double displacement equations. So that's what you're doing. And then the critical thinking questions refer to not just the first part, where they say, supposing, a different metal like iron reacted with silver, where would you place it in the list of metals from most to least or least to most? So you can think about how iron, a metal that's not part of this experiment, would be ranked, again, in that critical thinking question. And then the other critical thinking questions ask you about this table. They say things like, if you had two things that were mixed up, two chemicals that got mixed up. So you've got, I think it's zinc and potassium, maybe something like that. And they said you have two bottles, you don't know how to tell which is which. What can you add to them to be able to tell which is which? And so if you go down and you just compare the columns or the rows for zinc and for potassium, we see that they're both soluble with chlorine, they're both soluble with sulfate, they're both soluble with acetate. But right here, we see that zinc, when paired with a carbonate, would form a solid, where potassium, when paired with a carbonate would not form a solid. So theoretically, if we had two bottles, one of potassium, one of zinc, and they were unlabeled, we could add some carbonate to a small portion of one of them to see what would happen, and by doing so, identify the unknown, or identify which bottle we're actually reacting with. So we could use this table, and that's what they want you to do on those critical thinking questions. Okay, I hope that helps. I hope this gives you a little bit of guidance, but email me if you have questions. All right, see you guys.